Okay, so 2.1. We are in another chapter of 105. So, this chapter, we're going to start looking at a new topic. We're still working with linear functions and whatnot, but what we're going to do now is going to look at data, and we're going to look at mathematical modeling, at least in the most simplest sense that you can think of. So this is a very heavy calculator chapter. Not all the sections are calculator heavy, but there are a lot of different things you could use your calculator for in this chapter, and we're going to look at that. So what we're going to do in the first section of chapter 2 is we're going to look at, if you think back to the very beginning of the first chapter, so 1.1 we used qualitative graphs. That was graphs without any axes on them or any units on them. Well, now we're going to look at graphs, but now we're actually going to plot values on them. And those kind of graphs are called scattergrams. They're also called scatter plots. You may hear me say scatter plot in lieu of scattergram from time to time, because I'm used to saying scatter plot, but they're both the same thing. So a scatter plot, all it really does is it displays raw data from a given experiment or from a given study, and it displays them on the graph in a way that shows where each ordered pair is located on the scatter plot. So if we look at this raw data here, this data measures the numbers of Grand Canyon visitors for various years, and this is the source that was given. So here's the year 1960, and this right here represents 1.2. Now, if you notice here, this is the number of visitors in millions. So what this really is saying is in 1960, there are 1.2 million visitors to the Grand Canyon, and so on. 1970, 2.3 million, and so on. We abbreviate it with millions so it's easier to work with in the data. We'd rather write 1.2 than 1,200,000. It's easier to work with. Okay, so now that we have our data here, what we want to do is we want to make a scatter plot. So the first thing we need to do, when we make a scatter plot, the first thing we need to do, we need to clearly define which value is the independent and dependent variable. And that way we can organize our data. So now, typically the left column is the independent and the right column is the dependent variable, but we want to make this abundantly clear. And we want to describe what the variables are measuring, or how the variables are going to be measured. So in this little space right here, I'm going to define this. This is the independent variable. And since it measures years, I'm going to use a variable t, right? T for time or years or whatever. So that's the letter I'm going to use. I'm going to use t for time. So I'm going to let t be the number of years since the year. Now, since our first year is 1960, I'm going to say since the year 1960. So this right here will be the value variable t. Okay. Now I'm going to let the number of visitors in millions, I'm going to let a variable represent that actual value, the number of visitors in millions. So, and since this data is displayed in a acceptable format, I'm going to leave it as is. I'm not going to actually, if I just go back to t, I just look at this data, instead of saying it's the actual year, I'm saying it's the number of years, because that, the number of years is usually more acceptable when it comes to making data or representing data. So I'm going to let, so if I jump ahead in the notes a little bit, I think they use the variable v. They do, and I'm going to use that as well. But just keep in mind that you don't have to use the variable v. They let v for visitors. You could use n for number. It's up to you. I'm just going to let v be the number of visitors to the Grand Canyon for a given year. So this right here is the number of visitors, letter V. Okay, so now that we've clearly defined our variables, we're letting T be the number of years since 1960 and V be the number of visitors to the Grand Canyon for a given year. Now we're ready to collect our data. You're probably wondering, well, don't we have our data right here? Yes, this is our raw data. We do. This is our raw data, but based upon our variable's description, it may or may not be the data we're going to plot on our scatter plot. We have to modify this data to represent our variable's descriptions. And that's what we're going to do on the next page. So if you look at the next page, on page 2, so this table that I have right here is the raw data that was on the previous page. I just have it for reference so we don't have to keep flipping back. So now, based upon those variables descriptions, I'm going to take our raw data. All right, this is just a copy of the raw data. That's all it is. And I'm going to convert it into the data based upon our variables description. Now I have them labeled right here. T is the number of visitors since 1960. And V is the number of visitors in millions for that particular year. So now let's convert the data, the raw data, into the data based upon the variable's description. So 1960 is how many years since 1960? Well, that's pretty obvious. 0. 0 years have elapsed since 1960 in the year 1960. Okay. How many years is 1970 from 1960? That's 10. And if you keep following the data, you can see that it's going to be 20, 30, 40, 50. So this is the data based upon our variable's description. Now the number of visitors in millions, well, there's nothing changed here. The number of visitors in millions, V, is defined as the raw data is given. So we're just going to copy this down. 1.2, 2.3, 2.6, 3.8, 4.8, and 4.4. So this is the data based on the variable description. Okay. So now that we have this, converted data, we're now ready to make our scatter plot. So each one of these is the ordered pair. So this is going to be an ordered pair 0, 1.2, and so on. I just won't have the space because of this, but you get the idea. So, and this will be 10, 2.3, and so on. So those ordered pairs are going to be plotted below. Now, when we make a scattergram, we have to have a consistent unit. We have to have a consistent, what's the word I'm looking for? We have to have consistent tick marks on our axes. So, okay. So remember, independent variable, horizontal axis. So this is T, this is V. Don't forget to write their titles on the axis. So T is the number of years since 1960. V is the number of visitors to Grand Canyon for a given year. Okay, so now that we have that, now before I start plotting my ordered pairs, I want to think of an increment size on both axes. So let's look at our data. So if you look here, t goes in increments of 10. 0, 10, 20. So it's probably a good idea to go in increments of 10 on the t-axis. So let's do that. So that'll be 10. That'll be 20. That'll be 30. That'll be 40. And that'll be 50. And if we look at V, well, this goes from 1.2, 2.3, 2.6. So we have decimal values. So increments here in, like, I suppose increments of 1 is perfectly fine. So we'll go in increments of 1. So 0 to 1, 2, 3, 4, 5. Okay. Now that we have our axes filled out, now we can plot the ordered pairs. So 0, 1.2. So 0, 1.2. That's roughly going to be right here. Ten, 2.3. So there's 10. 2.3 is roughly right there. 22.6, which is going to be roughly there. 33.8. 33.8 will just be right underneath 4. 44.8 will be right underneath 5. And finally, at 50, 4.4. So 4.4 is going to be a little bit lower, so right about there. So this is a scatter plot, a rough scatter plot of our data, drawn by hand. You know, nothing too fancy. It's easy, you know, it's easy enough. But while this, while this is certainly acceptable, whenever you draw something by hand, it's not always accurate. So there's a way you could do this in your calculator. And actually, the scatter plot we just made is right here. Now, I'll get to what these lines represent in a minute, but you can actually make this scatter plot in your calculator. So I'm going to show you how to do that. Alright, so when you turn the calculator, here's what you do. So the first thing you want to do in your calculator is you want to type in your data. You want to get your data in, the described data. So to do that, you're going to go to Stat. See the Stat button? You're going to press that. And then you're going to go to the Edit button, which is the first thing that's highlighted. So just hit Enter on that. So hit Enter. And, well, you can see that there's already data in there from a previous experiment. So this takes you to lists in your calculator. You could press the right arrow and you'll go through all these different lists. So to clear the data in the list, so just go up and highlight list 1 and just hit the clear button. Do not hit the delete button. If you hit the delete button, it'll delete the list. You'll have to get it back by rebooting it, but just hit the clear button. So hit clear and then hit enter. and it'll clear everything in list 1. Highlight list 2 and do the same thing. Clear, enter. Alright, so now you could type in the data. You could type in the data into list 1 and then type in the other data into list 2. So let's do that. So 0, enter, 10, enter, 20, 30, 40, 50. Okay, now let's go over to the right. Now let's type in the visitor data. So 1.2, 2.3, 2.6, 3.8, 4.8, 4.4. Okay, so now that we have our data in, now we have to actually plot the scatter plot. So in order to do that, you have to turn the stat plot on. So the next thing you're going to do is, you see this word right here, stat plot, right above y equals, you're going to go to that. So you're going to hit second, y equals, and you'll notice you have 3 stat plots. We only need 1, so I'm going to turn the first one on. It needs to be on. So hit enter there, and then it's blinking on the on, so just turn it on, hit enter. Now it's on. Now you'll see this type. By default, this right here is a scatter plot. By default, scatter plot should be highlighted, but if it isn't, make sure it is. 99% of the time it's already highlighted. If you look at this, is a this right here is a histogram. That right there is a bar gram. And this right, like if you go right below it, these are actually bar and whisker plots if you've taken a stats course before. And X list is the data in list 1, and the Y list is the data in list 2, which is what we have. The mark, that's just the type of mark you want to see on your scatter plot. It doesn't really matter which one. I used the first one, which is the box. So now that we have that, we have the stat plot turned on. Really, the big thing here is to make sure the stat plot is on. That's it. And to make sure you have the stat plot on, not anything else. Alright, so now I'm going to do is I'm going to go to y equals, and I'm going to clear anything I have out of here, because I don't want that to show up on my stat plot. I don't want that to show up on my stat plot. So now let's actually graph. I want to actually graph this data. I have my data in, my stat plot is on, so now I got to use the stat plot. So to do that, you don't go into graph or y equals. You go to zoom, which is this middle button here, and you go down to number 9, which is zoom stat, or you could just press number 9. When you go down to it and hit enter, you'll get your scatter plot right here, and there it is. And if you look at it, you know, it looks pretty, it looks rather comparable to what I made by hand. If you want it to be like dead on accurate, go to the window button and make the units the same as what I did here. So since my X scale went from 0 to 50, I'll make this from 0 to 50, and they went in increments of 10, so my X scale will be 10. My Y minimum, well, the smallest value could be is 0, right? So I'll do 0, 2, and I go up to 5. I go a little bit beyond 5, so maybe I'll make it 5.5. And I go in increments of 1. So now when I go to zoom stat, there we go. It's a little bit more comparable to what I have graphed on the paper, as you can see. So now the X and Y axes are scaled exactly what I have on this sheet of paper. So yeah, there's my scatter plot. You know, once you get the hang of doing it, it's really not that bad. Just make sure that y equals is cleared out, because if it's not, that graph will show up on the scatter plot, and we will do that later in the chapter. Make sure your data's typed in correctly. You don't have too much data, or you have to be careful how you type it in. You don't get careless, and make sure your stat plot is on. The biggest thing that students forget to do is making sure their stat plot is on. And another big thing I see all the time is when you go back to y equals and you just want to graph this, you get an error message because you didn't turn your stat plot off. Whenever you go back to y equals, you got to turn this back off. Otherwise, you'll get an error message. Okay. So yeah. So that's it when it comes to making a scatter plot. So now what we're going to do is we're going to go on to the page 3. And we're going to start talking about modeling as a result of this. So these solid dots here, that's my scatter plot that I just made on the paper and in my calculator. Those are the scatter plots for my data. So here's a question that I want to ask. Can we draw a line that goes through all the ordered pairs on our scattergram? And the answer to that question is no, we can't. It should be pretty obvious, right? All these dots are all over the place. In order to draw a line that goes through all of them, they would have to be on a straight line. But these dots cannot form a straight line. It'd be zigzag. We can't do that. So, if we were able to draw a line that went through all of these points, it would be a perfect model. But modeling and perfect don't go together. Remember, a model is an approximation. If you're approximating something, it's not going to be exact. So what we could do is we can make a bunch of lines that represent the data as closely as possible. So when I printed these notes, I printed them in black and white, but these lines, if you look at some of the copies on Canvas, they're probably in color. So I'll just reference that here. These lines are actually different colors. So what I'm going to do, and the reason they're different colors is because they differentiate. Each one represents a different model. So what I'm going to do here is I'm going to call this one Model 1. This one Model 2. And that one Model 3. They all represent different models because they're different lines. Now, I want you to notice something here. Notice how these three lines on the scattergram do not go through all the ordered pairs, because I already said that. It's impossible. These ordered pairs don't form a straight line. But they do go through some of them or none of them. So here's the description of modeling. And this process is called modeling. Modeling is a process of seeing which one of these three models comes as close to these data points as possible. Now, could I make another model, like model number 4, that would do even better than these three? Possibly. But it seems like these three models are the best models that I can make for representing this data. So finding the best model that illustrates the data, that process is called modeling. That's finding the best model to represent the data. Finding the best model to represent the data, that process is called modeling. Some people might choose Model 1. Some might choose Model 2. Some might choose Model 3. Without eyeballing it, you can't tell which one is the best. There are some other, mathematical things we have to do to determine that, but it's more of a instinctive thing to do. Just by looking at it, you're probably thinking, all right, I'm going to say Model 2. I'm just going to say Model 2. But again, it may be Model 1 that's the best, but either one of these models do a good enough job to represent our data. This process is very similar to like a meteorologist. Say it's like the month of January and there's a snowstorm coming for Pennsylvania. meteorologists all over the state, or even in the region, are looking at weather data from weather models, and they're plugging it into some, weather computer system, some weather computer system, and that computer system is going to tell the meteorologist, all right, we can expect anywhere from 10 to 15 inches of snow. Now, there might be, let's say there's like 100 models, 100 different models that the meteorologists use. If 95 of those 100 models are going to say 10 to 15 inches of snow, but one model says we're going to get 2 feet of snow, and 4 other models say we're going to get 3 to 5 inches of snow, what do you think the meteorologist is going to say when he goes on the news and says, all right, I can expect how much snow? He's going to say 10 to 15 inches because the majority of the models indicate 10 to 15 inches. That is modeling. Scientists, not just meteorologists, scientists in all different realms, physics, chemistry, biology, they do this kind of stuff all the time. They take their raw data from their experiment, they plug it into some computer program, and engineers or computer scientists, they run math programs that crunch the numbers and spit out a model. And that's how mathematics is done in the real world. So you just have to understand this concept, that the process of finding the best model is called modeling. That's all you have to understand. Okay, so I digress. Let's keep going. So, this might be obvious, but these are lines. So these are linear models. There's other kinds of models out there. There's exponential models, quadratic models, and etc. I could keep going on and on, but in this course, all we're looking at is linear modeling. If you go to college algebra, you will see other types of modeling. So since those lines are straight, they are considered linear models. A linear model is a linear function that describes the relationship between two quantities for an authentic situation. So we can measure the number of years since 1960 and the number of visitors to the Grand Canyon as a linear model. So, a model is just a mathematical description of an authentic situation. We could describe this situation by a model. What kind of model? A linear model. That's it. That's all I'm saying. The big thing here is to understand what modeling is, what it represents, and that we're working with linear modeling because it can be formed by a line. Okay. So, on page 4, what we're going to do is now that we've looked at the process of modeling, now what we want to do is we want to use one of those models to make estimates and predictions about some future amount or some particular amount from that data. And that's what we do modeling for. Just like I said with our meteorology data, if we have weather data, usually, let me give you a different situation. Let me think about this. Let me give you a different scenario here with like a meteorology example. What if you're making a projection about the weather for next week? You're going to use a current model, and based upon the data in that model, you're going to make a prediction about the weather next week. You could go on your Weather Channel app right now and see what they think the weather's going to be next week. And it might be right, it may not be. We'll talk about that. We'll talk about, why it's wrong or could be wrong a little bit, but all I want you to understand now is we use models to make estimates and predictions. That's one of the the benefits of modeling. All right, so here's our scatter plot of our visitor data, and based upon this graph, it looks like we chose. It looks like my hunch was correct. We chose model number 2. I think so. Yeah, it looks like we chose model number 2. So someone decided to say, all right, we're going to use model 2. It doesn't mean that model 1 and 3 are wrong. They just felt like model number 2 was the best illustration of the data. Okay. So now we're going to use model number 2 to make some predictions. So let's look at question number 1. Use the linear model shown above to predict the number of visitors in year 2018. Okay. Well, if you remember, so we want to predict the number of visitors. The number of visitors is the variable V. 2018. So now this is the year 2018, but T represents what? Years since 1960. So yeah, this is talking about T, but is it in the proper description of our data? It's not. In order to put it in our proper description, we have to look at the number of years that 2018 is from 1960. So to do that, you just, find how many years 1960 is between 1960 and 2018. So 2018 minus 1960 is 58. So T equals 58. So this is 58 years since the year 1960. So now when I want to find V, I just look for the value T equals 58, go up to my linear model, and then go across to see what the number of visitors may be. So T equals 58 is, alright, so here's 40, here's 50. This is going in increments of 2, it looks like. So this is 52, 54, 56, 58. So that right there is 58, right? Let me use blue. So that's 58, so let me go up to my linear model here. And I hit it right there, right? Now let me go over until I hit my graph. And it hits right about there. Okay. So if this is T equals 58 and it goes up to the line there and it goes right around there, what value would you say that hits? So if this goes in increments of 0.5, it looks like this is 0.51, 1.52. So this is right between 5 and 6. So it looks like 5.5. So based upon this, it looks like V equals 5.5. So let me answer the question. So in the year 2018, there are, now since this is an approximation, I'm going to say there are approximately 5.5. Now remember, this isn't 5.5 visitors, it's 5.5 millions of visitors. 5.5 million visitors to the Grand Canyon. Alright. And that's it for question 1. I'm just using that model to make a prediction. And let's look at question 2. So use the linear model shown above to estimate in what year there were 4 million visitors. Okay. So we want to estimate in what year. So that is talking about the variable t. There were 4 million visitors. Well, that's saying that the value v is equal to 4. Right? So in this problem, I'm not starting here. I'm starting here. I'm going over to find the value of t. So v equals 4 is over here, right? So let me go over to my model, and I hit it roughly right there. Maybe a little bit more. Right there. Okay, so now let me go down from there and see which t value I hit, roughly. So when I go down from that, roughly right there. So what value is that? Well, 30, 32, 34, 36. It looks like it's just below 36, so I'm going to say 35. But if you say 36, that's okay. It's close enough that 35 or 36 is going to be good enough. So I'm going to say 35. So that's roughly 35. So I'm going to say that that is roughly 35 years. So this is 35 years since 1960. So what year is that? Just add 35 to 1960. And that's the year 1995. So to answer the question, there were 4 million visitors to the Grand Canyon in the year 1995. And that's it. So this is one way we could use a linear model to make some estimates and predictions. Now, you know, that's good and all, but now a little bit later in this section, I believe it's in this section, just give me a second. Actually, yes it is. A little bit later in this section, we're going to look at, what if we want to make a prediction about something that's way off out here? What if we want to do something that's way off out there? Or way back here? Is it going to be accurate or not? And we're going to look at that in a minute. Alright, so let's go into the next page, page 5. Alright. So, remember how I mentioned a little earlier that, you know, there are all different types of modeling? The only modeling we're going to look at in this course is linear modeling. Well, I want you to be able to understand the difference between linear modeling and other types of modeling. You know, how do we know a linear model is a good way to model the data? Can it be described well by a linear model? Just because we have a model doesn't mean it's linear. We have to make sure it looks like a linear model. So our goal here is not to try and find a line that contains the greatest number of points. The goal is to find a line that comes close to all the data points as much as possible. So, you know, if I look at these three different plots here, this is plot A, B, and C, right? Well, it should be pretty obvious that, you know, plot A is a pretty good linear model because the data is pretty close to a, you know, it's pretty close to being a line. So if I were to draw a line through here, right? my line could look like this. That's represented pretty well by a linear model. But if I look at B, and I drew a linear model, that doesn't do a very good job. You know, this actually is quadratic. And C, you know, I could make a linear model here, but I could also, you know, I could try and make a linear model here. Or I can even go over here a little bit. C is a little bit more spread out, so C is better than B, but it's not, but A is the best of all of them. Okay. So how do I describe this? So A is described very well by a linear model. B, on the other hand, not linear at all. This one's actually quadratic. And C, well, it's neither quadratic, but I'll just say it's a poor linear relation. I mean, I guess C could be described linearly, but it's not very good. It's not very good. So this is a weak linear relationship. There's actually a value. There's actually a value that your calculator spits out, and it's a value that you can calculate in statistics. It's called the linear correlation coefficient. And even though this isn't in your notes, I'm going to write it down anyway. There's something called a correlation coefficient. And this coefficient, what it does is it measures the strength of the relationship between the two variables. You know, how good of a job does that particular model do at describing the data? And the correlation coefficient does that exactly. It measures the, quote, strength of the relationship described by the model between the two quantities studied. It's not a big deal if you don't see it in this course, but this linear correlation coefficient, it's actually described by the value R. And it takes a value between -1. Here's the inequality symbol again. R is caught between +1 and -1. That's what the linear correlation coefficient. R could be any value between -1 and 1. Alright, well, what does that mean? It means that the closer R gets to 1 or -1, the stronger the linear relationship is. The further away it gets, in other words, the closer it gets to 0, the weaker the linear relationship is. So I'll just say down here, the closer R gets to -1 or 1, stronger the linear relationship is. And the closer R gets to 0, the weaker the linear relationship is. So basically, the closer R gets to 1, the better it is. The closer it gets to 0, the worse it is. So why negative? Well, I'll just put like a little subnote here. 1 means positive linear. -1 means negative linear. That's all it is. Positive linear means it goes up from left to right. Negative linear means it goes down from left to right. That's it. But the closer it is to 0, the weaker it is. So if I come back up here, this one's pretty good. So the R value here, could probably be like 0.96 if I had to guess. Here it's pretty bad. So the R value here might be like 0.05. Here it's pretty average. It's pretty weak. So R here is probably 0.4. It's better than B, but not by much. But R is really good. These are just estimates based upon that. But your calculator actually could spit this value out. And, you know, I guess, excuse me. I don't think I'll do that now. Excuse me. I don't think I'll look at linear correlation coefficient right now. I'll wait till we actually get to it. But just keep in mind that this is a value you could see when you're doing linear modeling, especially in your calculator. In statistics, you'll learn how to compute this value by hand, even in calculus, if you're going to go that far. But, all right, that's all I wanted to illustrate there. Now, intercepts of a model and model breakdown. So the last topic in this section deals with intercepts of a model and model breakdown. Okay. So what is that? Well, we know what intercepts are. We know what the intercepts are. The intercepts are the points where the graph crosses the x or y axis. What is model breakdown? All right. Well, so even though a model may describe a known data set very well, it may not always yield results that make sense. You know, your model's no good if your prediction doesn't make sense, right? Like, you know, let me go back to my meteorology example. It would be pretty silly if your model said we can predict -5 inches of snow. You know, that doesn't make any sense. So you would look kind of stupid if you went on the TV and told everybody, hey, we're getting -5 inches of snow. Your model result has to make sense. So if you get something like that that's weird, that's an example of model breakdown. That's one example of a model breakdown. You get some result that doesn't make sense. Or if an estimate that is not a good approximation. So remember how I said earlier, like what if we want to make a prediction? What if I go back here a little bit? What if I want to make a prediction about data that's way off in the future or in the past? You know, if I go too far into the future, my data may not be accurate to predict that. Like, you know, in other words, I may know what the weather will be 2 days from today, but if I use my model to predict the weather 2 months from today, that's going to be less accurate. I don't know. It's too far in the future. So that's another example of model breakdown. Okay. So let's look at another type of data set. So this data represents the percentage of cell phone users who send or receive text messages multiple times per day. Alright, so here's the variable's description right here. The problem tells you right now. We're letting P be the percentage of cell phone users at age A. So P is the percent, so this is the variable P. And the age, to represent the age group in years, is right here, age A. So we're letting, for this age group, we're letting 21-year-olds represent that age group. So this says that 76% of 21-year-olds send or receive, this should say text, messages multiple times per day, and so on. So 63% of, roughly 30-year-olds send or receive text messages multiple times per day, and so on. So, okay. So we're, that's not in our model, that data. It's these two columns right here. So, some person, all right, so they make a scatter plot with this data. There's the scatter plot. They find a model. Here's a model that represents the data. Okay. So given this model, here are the intercepts. The model crosses the p-intercept right here. And that's the point. It's very hard to see, but this p-intercept, because it crosses the p-axis, is 0,106. That's the p-intercept. And the model crosses the a-axis right here. That's a little bit better to see. That's 71,0. Okay, so given our model, answer the following on the next page. Find the p-intercept. What does it mean in this situation? Has model breakdown occurred? And the same thing for question 2. Okay. So what was the p-intercept? The p-intercept was 0,106. What does it mean in this situation? You know what? Just ahead, I'll write down the a-intercept for the next problem. The a-intercept was 71,0. So, what does this mean in this situation? Now remember, the t, or not the t. This is a comma p, right? Independent, comma, dependent. So this is, what does A represent? It's the age, A years. And P represents the percentage of cell phone users. So A is the first coordinate value. So this says an age of 0 years. That's what this represents. This is an age of 0 years. Now, I'm just jotting this down to, show you what it looks like. And this right here is the percentage of cell phone users. Now I want to be able to interpret that. I want to interpret it. I want to interpret that. So what does this say? Well, this says, now there could be various ways to interpret this, but this says 106% of cell phone users at age 0 send or receive multiple text messages per day. And so that's what this p-intercept says. Okay. Has model breakdown occurred? Yes, it has. Why? Well, think about it. 106% of cell phone users at age 0. That's saying 106% of newborn children send or receive multiple text messages per day. That's not possible. Newborn children can't send text messages. So that's an example of model breakdown. Model breakdown has occurred. Babies can't send text messages. So yeah, that's definitely an example of model breakdown. Okay, let's go to the next one. So find the A-intercept. What does it mean in this situation? Has model breakdown occurred? Well, let's figure out what this means first. So this is the age. That's age 71 years. And this right here is the percentage of cell phone users. So let's interpret it. So this says 0% of cell phone users at age 71, right, send or receive multiple text messages per day. Is this model breakdown? Well, it is. This is model breakdown. Why is it model breakdown? Think about this result. This is saying that anybody at the age of 71 does not send or receive a text message. That's what that's saying. But we know that's not true. We know that there are some people that at least send or receive some text messages per day, even if they're 71 years of age. You know, I'm sure there are people at age 71 that do have at least a cell phone and they're using it. So, you know, you're bound to find at least one person, or at least 0.1%. So this is model breakdown. That's model breakdown. There are at least some people that use a cell phone. Just like up here, no newborn child's going to use a phone. So both cases are an example of model breakdown. Okay, so that is it for this section. It was, it was kind of a lengthy section, but it's just the idea of making a scatter plot, the understanding the process of modeling, choosing a good model, and making predictions of the model graphically. So in the next section, what we're going to do in 2.2, we're going to look at we're going to find linear models by hand or by algebra using techniques in algebra. Finding an actual linear function, a mathematical algebraic function, given a situation. And we already know how to find an equation of a line. Use the slope formula. Use one of the points, find the y-intercept, or you could use the point-slope form to find your equation of a line. We're going to do things like that in the next section, either with data or by a description. And that's what we're going to look at in section 2.2. So, yeah. So when it comes to the first section of chapter 2, you know, we're just getting our feet wet with the concept of algebra, or with linear modeling. So yeah, so that's the end of this video. That's the end of section 2.1.